Hi guys, Miss O'Connell here. So today we're going to be talking about the AP rotation test format. We'll talk about homework questions that we asked in the Google form and equations that we will need to use. Okay, so first things first, let's talk about the test format and the expectations. So test format. Your test is going to take place in class tomorrow. The format is going to be 15 multiple choice questions, okay, and 2 open-ended questions. So you will have both lab periods tomorrow to take the actual test, even though it's shortened. The AP exam is most likely changed to only open-ended, so we're going to focus a little bit more on open-ended as we move forward. So 15 multiple choice questions. Those multiple choice questions will be about on level with the Google form questions that have been asked over the past 2 weeks. So I took out most tricks from those types of questions just because I'm not physically with you to talk you through some parts. So they'll be more on level with the Google form questions. They'll be a little bit less complicated than the rotational dynamics multiple choice questions. What I mean by less complicated is that sometimes in the answers, they ask you to take an answer and then kind of convert it based on a constant they give you, which is just an extra trick. Okay, so there won't be an extra trick thrown in there. It'll be more, you still have to use things like the parallel axis theorem and finding moment of inertia for many objects, but there'll be less tricks in there, right? The answer that you get will be exactly one of the answer choices without manipulating any additional equations or substitutions in there. So they'll be a little bit less complex than the rotational dynamics, but similar to the Google Forms questions. Okay, open-ended. There'll be 2 free response questions. Okay, the free response questions will be a little bit less complex compared to the rotational dynamics free response questions. So what I mean by that is that it'll most likely be like question 1 on the rotational free response, parts A, B, and C. Okay, or question 3, parts A, B, and C, not D, E, F. Okay, so there will be less parts, less substitutions to make, but they will be on level with parts A, B, C, maybe even D, of those that were assigned on the rotational dynamics response. Okay, and again, a little bit less complex compared to the 2 from the test review. Okay, so again, you will still have the 90 minutes to take the test. You'll take it via Google Form. You will attach your work for the open-ended to Google Classroom. So all the multiple choice will be answered in the Google Form. You will type your answers into the Google Form for the free response, but you will upload pictures of your work and attach it to the assignment in Google Classroom. In that assignment, there will be a link to the Google Form and a link to the Google Hangout. So you will take the test on the computer, but you will have Google Hangout open on your computer. Okay, so that I can, 1, make sure that you are using only your note card and calculator, and 2, if you have any questions or need clarification, you can ask. Okay, I'll be right there. So again, you'll go on to the Google Meet, open the Google Form, answer all the questions in the Google Form, attach your work to the assignment in Classroom. Topics that are on the test. Okay, your rotational kinematics, which is finding omega, right? Finding alpha. If alpha is constant, there might be a few multiple choice questions like that. B is rotational dynamics. So finding moment of inertia, parallel axis theorem, linear acceleration or angular acceleration. Okay, so using torque equals I times alpha and F equals ma in conjunction to find A or alpha. Next, we talked about the conservation of energy. We must understand rotational kinetic energy, and that should say translational kinetic energy. So you must understand the difference between rotational and translational kinetic energy. Okay, one of the open-ended in the test review really kind of drove home that point. So please make sure that we took a look carefully at that open-ended question. Last topic we covered was angular momentum. Cross products for angular momentum will not be on your test. I will not ask you to find the cross product of two vectors using matrix determinants or your calculator. So that will not be on your test, but you could see it on the AP exam. That's why we reviewed it. For angular momentum, you should be able to find angular momentum for individual particles, which again, consult the Google Forms for examples of that, or conservation of angular momentum in systems. So there's one open-ended on the test review that's good for that, and then there's one in a Google form from last week that's also a good example of that. Okay, so let's take a look at some of the homework questions that we had. Okay, so homework questions that were asked in the Google form as of yesterday at 2 p.m. Test review, we have 1, 4, 5, and 1 and 2. Okay, rotational dynamics worksheet number 7, 11, 23, and 25. And then the rotational motion open-ended 2 and 3E. So technically 2 is not assigned. Okay, so if it's circled, ignore it. 2, there will not be one as complicated on the AP exam or on your test as 2. So we're gonna skip that question for today. So from the test review, the first multiple choice question. So basically, we're told that the system is in equilibrium, meaning that it is balanced at that fulcrum. So that means that the torque on the left must be equal to the torque on the right. Okay, so there will be a torque due to the force of gravity that's applied to the rock, and there will be a torque due to the force of gravity that's applied to the rod or the stick. In this case, the rod or the stick has mass, or mass that cannot be ignored. So we must include the force of gravity acting on that beam. The force of gravity acts on an object at its location of the center of mass. So for a rod or a beam, the location of the center of mass of that beam is directly in the center. So there are 6, let's just double count that, 1, 2, 3, 4, 5. There are 5 markings on the beam. We know that the first marking has a length of 0.2. So that means that the entire length, 5 markings, okay, the entire length of the beam is 1 meter. So the position of the center of mass for the beam is going to be 0.5 meters from its end, right? So the location of the center of mass is halfway along that beam. That's where the force of gravity will be applied. So the torque due to gravity on the rock is going to be the mass of the rock times gravity, which we assume is on Earth, 9.8, times the radius from the location of the mass to the pivot. And that's 0.2 meters. We don't know the mass of the beam, that's what we're trying to find, so we need to leave that as a variable. We know that G is 9.8, and that the radius, big R, the distance from the fulcrum to the position of the center of mass, which is the location in which the force of gravity will act, is 0.5 minus 0.2, which we get 0.3 meters. Okay, so from here to here is 0.5. We want from here to here. Okay, we know this is 0.2, so we need to subtract that from the entire distance. We get 0.3 meters. So we plug in 0.3 for R. And then we solve for the mass. So the mass of the beam must be 4 kilograms in order for the torque due to gravity on the rock to be equal to the torque due to gravity on the beam. Okay, so the answer there is E. So important point to remember there is that the force of gravity acts on the position of the center of mass of an object. Okay, number 4, still on the test review, multiple choice. We need the total moment of inertia for the rod and the point particle system, right? We're not given a radius, so we can assume that the radius is negligible and that only the mass will affect the rotation. So we need to use I of a point particle, which is mr squared. We're told the I of a rod is I dot O or sub O. So you plug in I sub O for I of rod, mr squared for the I of the particle. M technically we're told is 2m. R, the radius from the point particle to the axis of rotation, which is through the center of mass, is half L. So the radius from the point particle to the axis of rotation is 1/2 L. So you plug that in for R. When we square 1/2 L, we get 1/4 L squared. And then we simplify. So our answer is I sub naught plus 1/2 mL squared, and that is answer choice C. Okay, number 5 is a little bit complicated just because they throw a trick in there at the end. So we can absolutely do number 5. We've done several examples like this. So we have a disk that's radius r and has a moment of inertia I. Okay, so they give us I, so they want the answer in terms of I. Okay, when we use torque equals I times alpha, we know that the torque that causes the rotation in an outward machine is going to be labeled as positive. The torque that opposes rotation will be negative. Because M2 is larger than M1, torque due to M2, or torque sub 2, will be positive because it is in the direction of alpha, the angular acceleration. Because M2 is smaller, the tension at a radius, aka the torque, will oppose rotation, it'll be negative. So the sums of the torque will be T2 or tau 2 minus tau 1 is equal to, I'm going to plug in like we usually do, the value for I of a disk, which is 1/2 the mass of the pulley times r squared times A over r. Okay, one of the r's will cancel. You know that the torque is due to this tension at a radius and this tension at a radius. Okay, I just noticed something here. The first pulley where it says T1, that should be labeled as T2. T2. Okay, this is T1. I wrote two tau 2s here. Okay, so this is T2 at a radius r, because it's a positive tau sub 2. This is T1 at a radius r, gives us negative T1, or tau 1. Okay, when I plug in for tau 2 and tau 1, tau 2 is tension 2 at a radius r, so the tension due to mass 2 times radius of r, minus tension due to mass 1 times the radius of r. That r again will cancel. We have T2 minus T1 equals 1/2 the mass of the pulley times the linear acceleration. To get rid of T1 and T2, we move on to step 2 and 3. We use the linear version of the second law, F equals ma, to find equations for T1 and T2. We plug those in, and we simplify. We simplify and we get that expression there. M2 minus M1 times G divided by 1/2 the mass of the pulley plus M1 plus M2, which is not an answer choice. All the answer choices are in terms of I. So we must pull a trick here. So we know that I is 1/2 mr squared. Okay, we need I somewhere in the denominator. So what we're going to do, we know that I is related to 1/2 times the mass of the pulley. Okay, so I is given to us as a given, must be included in the final answer. So we need to find a way to get I into the equation via this outlet here, because I relies on 1/2 times the mass of the pulley. So I is 1/2 mass of the pulley times radius squared. Technically, if you take I and you divide by r squared, that's equivalent to 1/2 times the mass of the pulley. Okay, so if we substitute in for I, which is 1/2 mass of the pulley times r squared, and we divide by r squared, we get 1/2 times the mass of the pulley. So to equate I into this equation, we can plug in for 1/2 times the mass of the pulley. We can plug in I divided by r squared because it's dimensionally the same. Okay, so the answer choice is B. On a test or a quiz, okay, the answer would be what you solved for over here. There is no benefit in having this equation in terms of I and R. Okay, you want in engineering, okay, and in physics, you want the answer in terms of units or constants rather, which you can plug in easily and measure easily to find the answer. I is technically not a constant. R is just another constant that we'd have to measure. So there's no benefit in having the answer in terms of I. But unfortunately on the AP exam, they throw in those tricks to see how well you can perform dimensional analysis in a quick situation. So on our test or quiz, this would be the answer. Okay. But technically, if it gives you I, the answer needs to be in terms of I. To get I in the equation, you have to pull a fast one here. Okay, and the answer choice is D. Okay, so test review open-ended. So in the first question, we have a rod that swings on a horizontal table, and that horizontal table is frictionless. So we're looking at a bird's eye view. The length of the rod is L. It swings with an initial angular velocity of omega. The ball, or the point mass here, does not have an initial velocity or an initial angular velocity. We're told that the I of the rod is 1/3 m1 times L squared. So in the first part A, we're asked to find the velocity, the final velocity of the point particle in terms of m1, L, omega, and m2. So in terms of constants. So we use the conservation of angular momentum. Because there is no net torque acting on the system, we know that angular momentum will be conserved. So L sub I, we have I of the rod times the initial angular velocity plus 0 because the mass does not have initial velocity or angular velocity. At the end, the after picture, we note that the rod comes to rest and that the point mass instead gains that omega, that angular velocity, or that angular momentum rather. So we have 0 plus I sub point particle. We need to find V, so for omega, we're going to plug in V over R. Okay, so I of rod, we're told is 1/3 m1 times L squared. So we're going to plug that in for I. The I value for a point particle is mr squared, so we're going to plug that in. One of the r's will cancel. Note here that r is the radius from the axis of rotation, which is this pivot here, to the actual point mass. So that radius is the length of the rod. the radius is length of the rod. Okay, so it's the mass of the point particle times the radius from the axis of rotation to the actual object, which is L, the length of the rod. So we're going to plug that in for R, and then just solve for V. So we solve for V, we determine that the velocity of the point particle after the collision will be m1 times the length of the rod times omega divided by 3 times the mass of the point particle. Okay, and again, angular momentum is conserved here because there is no net torque added to the system, no net torque added to the system. Okay, and the torque is dependent on the pivot position, which is the axle that keeps the rod secured to the table. All right, part B. So we're asked to find the individual momentum before, the linear momentum individually before the collision. So you have the individual momentum of object 1 plus the individual linear momentum of object 2. Object 2 is not moving initially, so that linear momentum will be 0. We plug in m1 for the mass, and v1 initial is technically going to be the omega value, which was given to us as omega, times r. Okay, and the radius here is 1/2 L. Okay, and that's the distance between the axis of rotation and the center of mass. So when we simplify here, we get that the initial momentum is m1 omega times L divided by 2. Okay, and that answer is in terms of the variables that were listed for us, so that we're good and we can move on to part C. The final momentum of the system, okay, is the individual sums of the momentum. Again, we're talking about linear momentum. After the collision, the rod will have no linear momentum, only the point particle will have momentum. So you know that the final momentum will be m2 times the final velocity, which we solve for in part A. So I'm going to plug in V from part A into part C and simplify. The m2's will cancel, so you get that the final momentum of the system, linear momentum, is m1 times L times omega divided by 3. Okay, so parts D and E. So part E is, we should not have had a problem with. Okay, so the angular momentum about the pivot position, which is point O in the diagram, is conserved as the net torque on the axis before and after the collision is internal to the system. Okay, so there is no external torques acting on the axis of rotation. So the angular momentum is conserved. However, the reason why the rod comes to rest has to do with the force of the pivot on the rod, which is technically, if we're talking about linear momentum, the collision occurs between the rod and the object. Okay, so the pivot force on the rod and the rod's force on the pivot, which are technically equal in magnitude but opposite in direction, are external to the particle and rod system. So linear momentum is not conserved. As the pivot applies the force on the rod to change its motion, the force of the pivot is external to the mass rod system. Okay, so the difference between angular and linear momentum here, right? Angular momentum is conserved about the pivot position. So the net torque applied to the pivot before and after is internal to the system. When we're talking about linear momentum, the collision occurs between the rod and the particle. The pivot is outside of the rod particle system, and its force does affect the motion of the rod. So linear momentum would not be conserved, but angular momentum is conserved. Okay, open-ended number 2. So we're given I of the sphere is 2/5 mr squared. We're told that the answers need to be in mass, radius, height, g, and theta. So part A is a little tricky. So we're taking the sum of the initial energy equals sum of the final energy. We need to find a value or an expression for V in order to plug in. So we're asked in part I, A sub I, we're asked to find the translational kinetic energy. In A sub II, we want the rotational kinetic energy. In order to get expressions in terms of those variables only, we first have to use the conservation of mechanical energy in order to find an expression for V squared. So we know at the top of the hill, we have gravitational potential only. At the bottom, we have rotational and translational kinetic energy. We plug in for I, which is 2/5 mr squared, and for omega squared, which is V squared over R squared, and then we simplify and we solve for V squared. For V squared, we get the expression 10/7 G times H. We know that translational kinetic energy is 1/2 mv squared, so we're going to plug in that expression for V so that our answer is in terms of the correct variables. When we simplify, we get 5/7 m times G times H is a translational kinetic energy. Okay, so A sub II, this is a little bit tricky. So we know that the total energy needs to be equal to mgh. We know that mgh must be equal to the translational kinetic plus the rotational kinetic. We just found in part I that the translational kinetic is 5/7 m times G times H, and we need it in terms of those variables only. So if we use that conservation of energy equation and we subtract 5/7 mgh from both sides, 7/7 minus 5/7, we get 2/7 mgh. So the expression for rotational kinetic energy in terms of mg and h is 2/7 mgh. Okay, in part B, they ask us to find an expression for the linear acceleration and then an expression for the force of friction. Okay, in terms of those variables only. So we're going to have to set up a system of equations there. We know that the force of friction is what causes rotation. Right? Without friction, it would slide down the incline. The reason why it rotates is because the incline has friction. So the torque is due to friction. So force of friction times the radius equals 2/5 mr squared times a over r. Right? So we're plugging in for I and for alpha. The r's all cancel, and our equation simplifies to the force of friction equals 2/5 m times a. We need to use the linear version of Newton's first law, or second law rather, F equals ma, to find an expression for the force of friction. So in the x, right, if we flip the axis, sine, or x is cosine unless it's on an incline, right, sine slides. So we have negative force of friction, which will oppose the linear motion, plus the x component of the force of gravity, which is mg times the sine of theta, equals m times a. So we're going to manipulate that, solve for force of friction. We find that the force of friction is equal to m times g times the sine of theta minus m times a. We then substitute that expression back into the torque equals I times alpha equation, and we solve for the linear acceleration. We find that a is 5/7 g times the sine of theta, which is in terms of the correct variables that were listed for us in the beginning, so we know we can box our answer. In B part II, we need an expression for force of friction in terms of only those variables. So we're going to take that equation, force of friction equals the x component of the force of gravity minus m times a, and we're going to plug in for a using the expression we just solved for to find that the force of friction is 2/7. The magnitude of the force of friction is 2/7 m times g times the sine of theta.